sixth-generation fighter jets are not merely a continuation of their predecessors. They represent a paradigm shift in military aviation. While the fourth and fifth generations focused primarily on extreme maneuverability and passive stealth, the sixth generation shifts the center of innovation toward artificial intelligence, AI integration, autonomous systems, sensor data management, and non-conventional aerodynamic designs. In this context, China has emerged as one of the most aggressive and ambitious actors through two parallel projects, the Shenyang J-50 and the Chengdu J-36. China's aerospace industry is attempting to build the foundation of its future air power. These aircraft are designed not just as fighters, but as network-centric aerial combat system platforms. On December 26, 2024, these two prototypes reportedly conducted their maiden flights. This date carries symbolic weight, coinciding with the birth anniversary of Mao Zedong. However, beyond the symbolism lies a far more vital strategic message. China is openly demonstrating its technological readiness for the sixth-generation era. Why two jets simultaneously? A fundamental question arises. Why is China developing two sixth-generation fighters at once? Wouldn't a single project already require massive costs, thousands of experts, and years of research? The answer lies in China's unique approach to strategic technology development, structured internal competition. The government does not appoint a single manufacturer as the winner from the start. Instead, two giants, Shenyang Aircraft Corporation and Chengdu Aircraft Corporation, are given space to compete directly for the same objective. This model fosters diverse technical solutions. If one design proves superior in a specific aspect, it can be prioritized. If both have distinct advantages, they can be operated in complementary roles. This method mitigates technological failure risks while accelerating innovation. Differing design philosophies. The differences between the J-50 and J-36 are rooted in the history and character of each manufacturer. Chengdu Aircraft Corporation is known for developing relatively lightweight, agile aircraft. This lineage includes the J-7, J-10, and the fifth-generation J-20 stealth fighter. This philosophy is reflected in the J-36, designed for agility, flexibility, and high maneuverability in complex combat environments. Shenyang Aircraft Corporation specializes in large, powerful, high-speed aircraft, such as the J-8, J-11, J-15, and J-16. This character defines the J-50, which focuses on speed, long-range endurance, and air dominance based on extreme stealth technology. Sixth-generation stealth concepts. A primary feature of sixth-generation jets is a more comprehensive approach to stealth. In the fifth generation, stealth relied heavily on airframe shape and radar-absorbent materials. In the sixth, it evolves into multi-spectrum signature management, covering radar, infrared, acoustic, and electromagnetic signatures. The J-50 exemplifies this through its tailless design. In conventional aircraft, vertical and horizontal tail fins provide stability, but they are highly effective radar reflectors. By eliminating the tail entirely, the J-50 is designed to significantly reduce its radar cross-section, RCS, making it much harder to detect and track. Eliminating the tail increases instability, especially at low speeds during takeoff and landing. To overcome this, the J-50 relies on 1. Advanced aerodynamics, a lambda wing or cranked aero configuration that merges with the fuselage to reduce drag. 2. Swiveling wingtips, movable wingtips that act as a substitute for the tail, controlling pitch, roll, and yaw. 3. Computer-driven flight control, systems that constantly calculate aerodynamic conditions in real time. The role of artificial intelligence. Without AI, designs like the J-50 would be nearly impossible to operate safely. AI serves as the central brain, integrating data from radar, optical sensors, infrared sensors, and navigation systems. It doesn't just assist the pilot, it can make autonomous decisions, allowing the aircraft to fly in semi-autonomous or fully autonomous modes for high-risk missions. Engines and thrust vectoring. The J-50 reportedly utilizes dual high-thrust engines equipped with two-dimensional thrust vectoring, allowing the exhaust direction to be manipulated for extreme maneuvers. The engine nozzles feature a serrated design to break up heat flow into small vortices, mixing them quickly with ambient air to mask the infrared signature from heat-seeking sensors. Diverterless Supersonic Inlet (DSI). To balance engine air intake with stealth, the J-50 uses a DSI system located underneath the fuselage. This placement keeps the sides of the aircraft smooth, preventing significant radar reflections from the side. A highly strategic design choice for multi-directional stealth. Network-centric combat integration. 6th-generation jets are viewed as major nodes in a combat network rather than standalone platforms. The J-50 and J-36 are designed to operate alongside combat drones, loyal wingmen, reconnaissance satellites, early warning aircraft, and ground defense systems. A loyal wingman concept. The J-50 or J-36 acts as an aerial command center, while accompanying drones serve as scouts, electronic jammers, or weapons carriers. Evolution of the pilot's role. Pilots shift from manual controllers to high-level decision-makers. AI handles basic flight stability and engine management, allowing the human to focus on strategy and coordination. Electromagnetic spectrum management. Modern warfare is fought in the realm of radio waves. The J-50 is designed to manage its own electromagnetic emissions, regulating its radar and communication levels to avoid detection, or even operating in a passive mode, where it only receives external data. Operational efficiency and logistics. Learning from the high maintenance costs of 5th-generation jets, China is employing a modular approach. Avionics and software are designed for easy updates without modifying the airframe, ensuring the platform remains adaptive to future technological breakthroughs. Sensor architecture. From fighter jet to information collector. In 6th-generation fighter jets, the primary advantage is no longer determined by a single superior sensor, but by an integrated sensor architecture. The J-50 and J-36 are designed as platforms capable of merging diverse sensor types into a single, unified situational picture. Radar is no longer the sole primary tool. These aircraft combine ASA radar, infrared search and track, IRSD sensors, electro-optical sensors, and passive electromagnetic emission receivers. All this data is processed simultaneously by onboard computer systems and artificial intelligence. The strength of this approach is the ability to detect threats without emitting active signals. In many scenarios, the aircraft can see the enemy without being seen, a principle that serves as the foundation of modern aerial combat. ASA radar and the role of AI. The active electronically scanned array ASA radar on 6th-generation jets functions as more than just a detection tool. It acts as a medium for communication and electronic warfare. With AI assistance, the radar can dynamically change its emission patterns to avoid being detected by enemy systems. AI determines when the radar should be active, when it should remain passive, and when it should share data with other units. This is a vast departure from previous generations, where radar was largely controlled manually by the pilot. On the J-50 and J-36, these radars are expected to be integrated directly into the airframe structure, eliminating protrusions that would otherwise increase the radar signature. Electronic warfare as a primary weapon. The 6th generation redefines electronic warfare, EW. While previously considered a support function, EW is now a primary element of the weapon system. Aircraft like the J-50 are designed to jam enemy radar, spoof signals, and create ghost targets. In other words, a battle can be won before a single missile is launched simply by neutralizing the opponent's systems. This capability relies heavily on AI to analyze enemy radar patterns and adjust jamming techniques in real time. Internal weapon systems. To maintain stealth, the J-50 and J-36 rely on internal weapons bays. All primary munitions are stored inside the fuselage rather than on external hardpoints. While this limits the number of weapons carried, it allows the aircraft to maintain an extremely low radar profile. For specific missions where stealth is not the priority, the aircraft can be reconfigured to carry larger payloads, demonstrating the modular flexibility of 6th-generation designs. Future hypersonic integration. A frequent topic in 6th-generation discussions is hypersonic weaponry. While not yet officially confirmed, the J-50's large and powerful design opens the possibility for integrating hypersonic missiles in the future. Utilizing such weapons requires ultra-precise navigation and targeting systems, another area where AI is crucial, as human pilots cannot process data manually at such extreme speeds. Cooling and heat management. As electronic systems become more advanced, heat management becomes a critical challenge. AESA radars, AI computers, and EW systems generate massive amounts of heat. 6th-generation jets are expected to use integrated internal cooling systems tied to the aircraft structure. Heat is not just dissipated. It is managed to prevent creating a detectable infrared signature. The serrated nozzle design of the J-50 is just one visible part of a much more complex thermal management system. Cybersecurity and software. An often overlooked aspect of these jets is cybersecurity. Because 6th-generation fighters depend entirely on software and data connectivity, they are vulnerable to cyber attacks. Consequently, the J-50 and J-36 are expected to feature multi-layered digital security, including high-level encryption and automated isolation systems. If an anomaly is detected, the system can sever external connections to prevent a remote takeover. Production and industrial scale. Developing a prototype is one thing. Mass production is a significantly larger challenge. These jets require extreme manufacturing precision, particularly regarding composite materials and stealth coatings. By involving two major manufacturers, China is testing not only the best design, but also its industrial capacity. The project serves as a test of the national supply chain, workforce, and production technology. Long life cycles and adaptation. 6th-generation jets are built to operate for decades. Therefore, their system architecture is open, allowing for seamless updates. Sensors, AI, and software can be upgraded as technology evolves, ensuring the aircraft does not become obsolete. The long-term strategic value of the aircraft lies in its inherent adaptability. Impact on aerial operating doctrine. The arrival of 6th-generation jets forces a total rewrite of aerial doctrine. Combat is no longer focused on one-on-one dogfights, but on system coordination. Aircraft, drones, satellites, and ground systems operate as a single entity. Tactical decisions are made based on collective data rather than individual intuition. In this framework, the J-50 and J-36 are not just combat tools. They are mobile aerial command centers. Conclusion. The emergence of the J-50 and J-36 marks a new phase in the global aerospace race. While the U.S. continues its NGAD F-47 program, China's dual-track development shows high confidence in its national industry. Ultimately, these aircraft are more than just new fighters. They represent a fundamental change in how air warfare is conducted. By integrating AI, network-centric operations, loyal wingmen, and multi-spectrum stealth, China is not looking for a single answer, but a diverse suite of technological solutions to dominate the skies of the future.